So hi, everyone. Hope you're all doing safe and doing well. My name is Stefan. I'm delighted to welcome you the second webinar in WellTech 2025, and thank you for taking time to join us. And we have exciting and informative session just planned for you, feature how to verify PPG wearable design and tackle LED and PD positioning challenges. And to give you a bit of my background, I have 3 years of experience in verification of PPG wearables. And because everyone knows it's become a hot topic in the last 5 years as the Apple Watch, launched with the PPG sensor, all the consumer electronics, they step into this. And besides just making entertainment and very cool tools, cool toys, they making it into a medical grade. So that's what we will be covering today, how to turn PPG-based wearable device into a mid-grade device. So our experience in WellTech give us the deep understanding as we learn and exchange ideas with the customers, which are the manufacturer in the medical industries. So now we'll be learning a lot of importance and the challenges associated with achieving a proper PPG monitoring. So today we will go through the common test solution available out there when it comes to PPG wearables, and followed by a basic concept of a PPG wearables and an overview of a major aspect of PPG performance testings. And then at the positioning of the WellTech solutions among all the available options and where this come from, how it originates. And finally, we explore the way out of the difficulty in verify the multi-channel PPG acquisition systems. In the end, we're wrapped up, and also we'll wrap up section by section, just keep you updated. All right, without further delay, let's go right in. So feel free to ask questions through our webinar using our chat function. We will have a dedicated Q&A session at the end to address as many of them as possible. Of course, due to the limited QA time, we might not be able to answer all the questions. So all the unanswered questions will be collected and answered properly in the PDF file, along with our material sharing over the weekends. And let's just dive right in. So wearable device that monitor heart rate, SpO2, or blood pressure are used plethysmography technology could detect blood flow changes using light sensor. So ensuring these devices are reliable in various conditions is critical for their effectiveness and user safety. Here are some common testing methods for PPG-based wearables. Clinical trial or clinical validation is the golden guideline. Directly compare the wearables reading against the invasive ABG test using CO oximeters. It is, of course, authentic but costly. Most of the manufacturers will take this approach at the end, or whenever they are confident enough to apply their applicant device or their prototype at each build. So this is what happens when you go serious for medical grade. This is the destination, we can say so. And for the grade card tester, is used to find out the SNR in the signal processing by the LED or the PD of the wearable. However, it is limited in defining whose faults or specific faults is LED fault or PD fault, because it's a loop test. You only know the answer is a good signal quality or terrible signal quality, but you couldn't find out what's wrong. Is it PD wrong or LED wrong? And the data verification, which non-stop refining SpO2 by sending the raw data to algorithm for the model training and get a feedback and refine, feedback and refine, feedback, refine all over and over again against the clinical database with the annotations. This is definitely scalable. You can run it with 10 milliliter data, but it's time and resource consuming to gather all diverse data because the data need to be cover the wide patient spectrum, not all about the healthy people, but we need to care the people who are in need. And system verification and using optical simulator behave like human tissues or human finger for various scenario. This is very highly effective for sure. You don't need to go big on the risk to take clinical trial or all the other, just to run it in your lab and make sure your electronic working good, and then you start to approach the reading towards the actual clinical readings. But however, the watch is become either aesthetic or they have more technology in, so there will be multi-position LED and PD. So that would require the modification for different wearable device designs. That's why this kind of the concept might not always work for all the wearable device. And personal try-on is just put in the wearable watches on your staff or the outsourced personnel, some company, they take this kind of projects from the consumer electronics manufacturers. So they collect data from the real user in various scenario, cost-friendly, compared to others. But sometimes limited by the health status of personnel, we don't get to easily collect or invite the person in the need of the healthcare to join this kind of the try-on. So in short, the optical simulator and database verification, they are cost-effective and allow rapid testings. And clinical trial is essential for ensuring the device accuracy and reliability. So as we are trying to avoid the major cost of the undesirable performance, we can refer to the breakdown schematic of the wearable device and take care of each part, electronic speaking. In the pulse oximeter function of the wearables, they are front-end LED and PD with a signal processor hardware and MCU to operate the whole system and algorithm, either MCU embedded or external from the cloud. So all you do is just upload everything here through wireless to the cloud, and the cloud will calculate it and download the data on your mobile phone. So in order to systematically examine each part and measurable and traceable instrument as reliable options, WellTech AECG 100 is the multifunctional test instrument that suits this purpose. So for the three essential of the PPG testing for SpO2, we are looking at the first one is the transmitter performance, which is the LED performance of the wearable device. So when the LED ons and send it to the ACG, the PD of ACG is being plotted to this kind of the window. So all the pulses are showing is actually the PD detection from the wearable device. So you can check if your LED behave as you designed, as you programmed, instead of how to wire your wearable device to oscilloscope to see the electrical signal at each square wave that you push your LED. Now it's on the PD sampling window of AECG 100. Second is the receiver performance, which is the PD and the signal process performance of the wearables. And when the LED of the ACG is sent back to the PD with this kind of the simulated, simple, repetitive, regular optical signal, if those were great to gather the quality signal, since the signal the quality is secured, the basic heart rate and SpO2 is not an issue. It can be calculated easily. But the last is the advanced algorithm, which is actually turn the wearable device literally smart, capable of standing the trial of the real world, because we know there are motion artifacts out there, the ambient noise out there, and there are profusion of the low perfusion index, also the skin pigmentation. And to adapt the patient diversity, database will do it as addressed before, and the more there is that can be database can be converted into an analog signal, which is the optical signal, again, through the simulators to the entire variables or the pulse oximeter function. So in this test flow, actually, the third part, it will actually put both the hardware and the algorithm into test at the same time. Is rather systematic. So now we can wrap up our opening by telling that from the initial loop test by the gray card tester to the later clinical trial verification, each method has its own scope application, advantage and disadvantage at verifying PPG monitoring functionalities in a wearable device. And the verification strategy that combines multi-method can help engineer balance accuracy, cost, feasibility to deliver more reliable wearable products. The three essentials of PPG for SPO2 are the wearables LED performance, wearable PD, and signal processing performance. Finally, the advanced algorithm performance, which is in these illustrations. And now this functional tester is what is ACG100 is positioned in all available test methods. So the ACG100 primarily originates from the concept of the functional tester in ISO 80601-2-61 to better understand where to apply the ACG in verification. Let's just go over the standard just a little bit. It starts at the Annex DD calibration standard. So the first, the committee, which is the IEC committee, allowed the use of the secondary standard pulse oximeter equipment, which is calibrated against CO oximeter for data collection on multiple patients. So instead of going through the clinical trial, which is invasive way, costly, time consuming, you can adapt the secondary standard. So that is a spare of investment, a capital for sure. It's a good news. It's a gospel for every manufacturers. And second, this method prepare a statistically proof for accuracy claim before the actual clinical trial. Then the clinical trial is the atrial blood test. There's an abbreviation called ABG test with controlled desaturation, where a healthy volunteer, of course, they're going to be healthy because they will put into a chamber. They intentionally control the desaturation of the air inside the chamber. So the clinical trial with the invasive measurement or non-invasive measurement can actually measure someone lower than 90%. And all we know, when you see the reading of you is less than 90%, sometimes less than 95%, we need to go to the hospital. And tests are going to happen in the controlled laboratory conditions. Yeah, so in this condition, we can minimize all the source of known error, which is like low precision motion artifact and ambient light. And some 510K approval in there, they will specify if this applicant device is applicable to those kind of the situation. If you manage to counter those error source, and you can make clear in your 510K that those things can be associated with your reading, and your reading is still reliable even though those situations happen. And this will be disclosed more about the setting of the labs in the Annex E3, which we will cover in a later slide. And no worry, we have this, the standard also shows us this kind of the secondary standard calibration has been last over 20 years and is make sure the reliability of the test, also the safety of the pulse oximeters. And yes, and this is the closed standard that the PPG wearables SpO2 meter can have. That's why most of the manufacturer refer to this one. And of course, the secondary standard and wearables is invasive. It's an indirect calibration. Error is unavoidable, so developer need to comment on the error in the statistic proof for sure. So this is the quick comparison of the lab setup. So it's in the NXEE guideline for evaluating and documenting SPL accuracy in human subjects. So E.3, it mentioned about the non-invasive lab testing on healthy volunteers. So it's already non-invasive. Another is also non-invasive way on the patient. So this is more in the clinical settings. So even both of them are taking the secondary standard. Here is more respect to what happened to the patients. Another one is about the control all the variants and factors. So here we have a minimal variability. And here the test result or calibration result might suffer because the circulatory instabilities. Even the place you place your probe, place your wearable device need to be concerned on the specific patient individuals. And so in the end, you might, in the real patient setting, you might need a lot numbers of patients to prove your accuracy plan because as a patient, you can imagine the patient you collect, they have they cover all the scenario that your product claim for. That's why you need to claim and accumulate more data that can make sense to your test results. But in the lab testing, because everything control, it was a minimum variations, a limited or just a defined number that can speak itself for the story. So it's much more straightforward. All right. So this is actually what happened in the way of the procedure. Is either which way, which is the healthy volunteer or the patient, either way. So what happens is that the applicant device can be a smartwatch, smart clothes, smart earphones, smart jewelry like a smart ring or just a heart rate tracker. They can put on the patients to get a reading like A, and then they put on the subjects, which is the secondary standard, which is 510K clear. Let's say it can be a very famous Neoco or Massimo or GE device. So both device put on the subjects and then they will get reading. So the device manufacturer will try their best to approach the A reading towards B reading. So here is already a lot of the saving from the invasive clinical trial because you are using a secondary standard, not hurting, also not hurting to your budget. But still, human subjects are involved. So it might involve still time and also the daily wages, hour wages for those patients or volunteers. So thankfully, the standard inspired the use of functional testers in Annex FF.5. And that actually helps, before you go for this, you can actually adapt the functional tester in your lab. Make sure your electronic work as you wish, work as is programmed, and then you can go for another one. So this is another spare of capitals. So you can consider it as a signal source. So and in the standard, it mentioned it as a test finger. Over here, have LED on one side, PD on a different side. So you can, mirror out, face towards the PD of the oximeter, also the LED of oximeters. Then they will get the reading to the applicant device and get the reading on the 510K device. And then it can compare. So it will save a lot of times, a lot of resources for the R&D developers. And so, because where are we talking about those, wearable device? Mostly they are reflecting PPG. That's why we need different interfaces instead of having the optics on a different side, we need optics on the same side. And this is how it might look like. A simulator or functional tester with optics on the same side. So they can take care of the optics on the same side over the wearable device. So as we going to use this, adapt this, how can we be sure this working great? So we can use a standard to have a functional experiment with the functional tester to see how it's working good for it. So, and then this is the finger socket, and this is the reflected interfaces. So that's why we would need a patch that can working reflectively with this kind of test interfaces. And then I will just using stopper setting and get the reading, setting 2, reading 2, setting 3, reading 3. And then if I can manipulate the reading of the 510K devices, and then this should be working properly just fine for these kind of secondary calibrations. So on camera, you will see, okay, let me check. Where? Okay, on the camera, let's pull it up here. Okay, in the back, this is something else. So, right. So on the camera, you'll see this is the Neoco PN10M. This is definitely a 510K device, and now I'm sending 98 signal to the Neoco device, and then I can switch it to 90 and see if this, reflectance testing interface can actually manipulate the reading of the 510K devices. And then in no times, we can see it lower down to the 90, 80, 98. So within the 90 to 80%, the tolerance of the pulse oximeter is 2% normally. So it's also acceptable. And then we can go even lower to 80. Give it some time to catch the new pulse coming from the ACG 100. And no worries. And later on, we will guide you through the GUI of the ACG 100. Right now, we just need to focus on the reading we try to manipulate. And right now, it is still 80. So from the 80 to 70, normally the tolerance is from at least 3%. Below the 70, it can be up to 20% tolerance. So right now we know that the ACG with this reflectance test interface working good just fine for the 510K devices. So here we can move forward. So once this is okay, and what's next? We can use this reflectance test interface to test the applicant device. So I would still setting one parameter and see if the applicant device show me a good reading, and setting 2, reading 2, setting 3, reading 3. If it's working okay, because I'll be sending the same setting that I sent to the 510K device. So this setting we should also get the applicant device read the same. And then for sure, if they are close, in a very, very highly correlated manner, and the applicant device can consider a verify. So this is the spirit of the secondary standard. And before we start having a demonstration on an evaluation kit from the ADI, you may just, kind of have a limp on it because it was on the background. It's a maximum reference design 104. If I go to the demo, which is a very impressive one, and let's just get to know how it works. So this is the working principle of the reflecting PPG simulators. The wearable under test over here, imagine this is a watch, they have a PD LED, they will keep sending LED pulse to measure the patient. So imagine if, for example, I'm using a strong red and weak infrared. So it will be go over, on and on and on, keep measuring the patients. And then this is their, between that, you can see the LED sampling frequencies, right? So in this frequency, you can see also on the PD of ACG, as I showed earlier in the schematic, we have a PD sampling window to plot the LED intensity from the wearable device under test. And as we are speaking, we are trying to sketch the curve. So the whole curve is what you can set and play from the ACG GUI. So let's just look at the moment that we're trying to sketch this section from the whole curve, and the ACG will know the corresponding LED intensity to sketch this curve. So in this case, it might be a strong, stronger infrared and weak red signal. So it's opposite to the LED intensity from the wearables. So over and over again, the whole curve will sketch on the PD of the wearable devices. So with this in mind, you can understand the following demonstration easily. So let's just pull up the maximum reference design interfaces, and on camera you see it. So right, let's just get it. So it's a very unique device that with one lead ECG simulation and the PPG at the same time. So a lot of the manufacturers adapt these evaluation kits as a reference for their products. Yeah, sometimes they just integrated the circuits. It's very helpful, shorten the product development processes. So here, this is the ECG and the PPG signal come from ACG, and ACG does has a function to output the ECG and the PPG signal at the same time with a control delay, which is the pulse wave transit time. You can set the PTTP or PTTF to time parameter here. So are we going to concentrating on the SPO2 testings, which is will ending up to this page. So this is the infrared reading and the red reading. So the ACG, we can switch to the dedicated SPO2 pages, and then we can use the sampling feature. Right. So this sampling, it will be keep happening, keep going on. And then if we can actually find the best moment is niches, and then we can bring it up. So this is what happened actually coming from the maximum reference design. So every cycle it will behave the same. So in the infrared channel is rather easier. Let's just understand the PD sampling from here. So every time the purple process is actually the infrared from the maximum reference design 104. And the red is our LED switch. So it's normally active high, but once we detect the LED pulse from the device, we will turn on by drop the voltage. Use the voltage to turn on our LED. So it will do 4 times as we detect 4 pulse in series each cycle from the wearable device. It does the same for the red. So we'll detect the red pulse from the wearables, and we will drop 4 times to turn on our LED 4 times to sketch the PPG curve on the signal processing power of the wearable device. As for here, many might wonder, will you also turn on the red when you sensing these? What's these? They are actually the copy of the infrared signal, because the red PD of the ACG system is wideband. It will receive the signal from all wavelengths. But our infrared PD is narrowband. It will only catch the infrared signal. That's why it tells AC system to respond and sync the LED properly so you can have a smooth simulations. Right, with this understand, or if you see this kind of pattern on the PD sampling window, it's good to go. So here, that's runs a simulation. So, right, so I was gonna stop here, and as we know, this maximum reference design is working much better in just lower LED intensity. Yeah. So it's all about the experience, and then we can set something. Maybe we give it 30 and we give it 10 just to at the start, and we run it. Sorry, let's run it. So this is as we're waiting for the new reading coming up on the maximum reference design, and let's just go over the interface just a little bit. So this is the last two is the same, red PI and infrared PI definitions. The AC of the red and the DC of the red, and we allow you to using the LED drive voltage to drive the LED to simulate the red signal. So right now, as I setting like this is the absolute parameter you actually output from the AC 100, and to these signal composed by these kind of voltage setup, you consider 85 by the maximum reference design 104. All right. So yeah, so it's 85. Good. And then we can run another one, which is we lower the AC intentionally. So what would happen? Guess. The SpO2 is going to be higher. How? Because you can see if you have a stronger AC, bigger AC, bigger PI, and bigger red PI costs to bigger R value. A bigger R value, consider the negative sign here, the SpO actually would be smaller. And I'm just reducing the AC, so you're gonna see SpO2 just greater. So it was 98, 95, and now it's coming to 90. Great. So unless we know that this evaluation kit from the ADI, the maximum reference 104, is proper design, following the science of the pulse oximeters. And then we might fail jumping one box to another box is kind of the, it kind of lengthy, and then we can just use the advanced feature, which is very helpful, with the SpO2 table. The outcome of this function is to get the reference R curve of this device. So we can make a table for today, like demo, demo for all. And just for example, I will just click 10 and 300, 100. That's what I did before outside. Now it was 30, right? And the last one is also 100. And we do get 85. Yes, have we all remember? And then we can enter another one. As I reduce using to 8, we got 91, right? As we all remember. So we can run another one. Yeah, just another one. Another one on the, so here, right? So we can copy paste it and see, let's get 6. So we will get even higher SpO2 because I intentionally reducing the red AC, right? So the last row is for us to manually enter your observation on the wearable device, and now is 95. So if we do have volatile wearable, we can have a test to covering SpO2 100 all the way down to 70. This is the common specification of SpO2 reading. So to save us, sometimes we have just prepare a table just previous for you. So I just did 6. Yeah. So as we will try to make the webinar short and sweet. So this is the table. Imagine it's working good. And what else? We will turn this table into a graph, and the graph is coordinated by SpO2 and R value. So how it's gonna be? This is the graph is the, let's understand R value. R value equal to PI divided by RPI. So each PI consists AC and a DC. So one R value can replace the first 4 parameters, as we all understood, right? So the graph is actually the SPO2, which is the R curve. So this coordinate by SPO2 against R value, and we scatter all the test points on the graph. And this is the first polynomial line, which also the regression line, the minimum distance to every point. So they can represent the characteristic of this wearable device in the post-oximeter speaking. So, but in some case, they're actually parabolic. So we can use a quadratic regression to get the line, and the equation is auto derived. So you can apply these to the SPO2 main interfaces by just upload it, and you shut the table. Now it can change. What we did before is that we changed different red AC and to try to test, how does Massey design 104 think this signal is. But right now, as we get hold of these R curve, actually the reference R curve, then we can whatever we want to see, let's say 95. And once I hit enter, the RAC value will be auto-adjust along the curve here from 9 to 5.8898. So just get few seconds, wait for the reference design 104 to respond to the new signal. Yeah, it's 1% off. Great. It's actually bright. And also we can drop down to 85, or let's go 80. Go just a little bit extreme. So here along the curve, the AC is tuned up. So what I'm doing here is what you might be doing on the golden sample of your wearable device that manufactured in a batch. So you pick a golden sample from a batch, let's say 50, and you take the golden sample, run such the SPO2 table to get the reference R curve over here, and then can use this to check the performance at each level. This is called repeatability. And then you can use the same curve to calibrate the rest of the device manufactured in the same batch. So the performance of these devices can be consistent as the golden sample. This is how the quality can be controlled. Right. So we managed tuning to 95, 90, now even 80s. Right. And then we can even play the road data, which is the clinical data you record by your watches PD, and then you replay it. So this is what happened when you are walking. And this is no longer a regular PPG signal, but a very random signal. So here we can use this with such a PPG recording with annotation, and then you could convert it into proper format, feed into the ACG, and these the curve can sketch on the PD of the wearable device, and wearable can measure PPG and give a diagnosis and compare with the annotation of the clinical reading, and go over and over. The algorithm can be improved cost effectively. So now we can wrap up that ACG. They have AC and DC of RIR, and they give the room for innovations. And each device tailored reference R curve can check the repeatability and reproducibility. As I mentioned, that golden sample at a different level and the same SPO2 level cross-check with everyone to make sure the consistency, which is the reproducibility. And user-defined waveform replay help with the algorithm, and also these with the intentional noise add-on, no matter the MEMS noise or white noise, ambient noise. Now, respiration can also be considered noise because what happens is that when we breathe in and breathe out, does affect the PPG signal adjust a little bit. So it can either remove it or extract it and calculate the breath per minute. So that's conclude that it's good news for the manufacturer. The standard permits the use of the secondary standard, and which save a lot, not only money, also the time from the primary and invasive approach clinical APG test. The human involved but the cost rather sparing secondary standard control lab condition or the patient-centric setup. And prior to do these kind of human-involved calibrations, it's a very strategic to using a functional tester, as mentioned in the standard. And rather than the transmitted test interface, here is the reflectance test interfaces. And we just using the very flexible parameter, a GUI, also the very helpful Taylor feature to support the development and quality control. So all the modulation can be simulated as well for breath per minute simulations, and also the ECG and PPG output simultaneous with control delayed that can help with the blood pressure or arteriosclerosis algorithm. Yeah, this is what happened when the blood vessel gets stiffened. So Rippling database is also very helpful. Yeah. So beside the data training on the model training, using this, they will also go through your hardware of the signal processing and the PD. That's actually rather systematic. So in the end, we will cover how we address the LED positioning challenge. You can see so many very fashionable wearable devices, and it became a cornerstone in the monitoring. And this device transformed from the simple heart rate monitor to a sophisticated health tracker capable of providing insight into the cardiovascular health, oxygen concentration, even the stress level. However, the effectiveness of the PPG sensor is heavily introduced by positioning of the LED and the PDs. Therefore, adopting the PPG sensor simulator at the moment with a simple LDPD position start facing challenges, because what we show you one side of LED, another side of PD optics, this doesn't work for those beautiful watches or beautiful tracker. So the challenge wasn't there when all the design are like this, LED and PD. So they can go through a mechanical fixture, arrive on the PD, and ACG will send LED through the mechanical adapter back to the PD. So this PPG simulation works. So we can summarize from the previous experience. I think this is the first 3 years of the wearables development. You just need to make sure the enclosure is there to avoid ambient noise. The shortest distance, so which means you're going to make your adapter thinner as possible. So the CMC of machining will help. On isolation is definitely need to be to avoid the direct reflection of the LED, which is give you the non-positive signal, create DC offset, and that will give you incorrect readings. So that's why the wall is very important. Your PD is supposed only receive the LED signal from the ACG, which is sketch the PPG waveform that you would like to. So this is the case study of the watch that function multiple channel PPG acquisition. You have a PD on the ring, also the 2 LED at the center. So through the mechanical adapter, this is the customized PPG window with a LED on the ring, but just one PD at the center. So from the explosive view, we can see the watch and the mechanical adapter as the standard main board, also the head. So the key to make the simulation still working for this kind of multi-channel PPG acquisition device is to customize the board. So within there, so we can have a closer look at it by seeing this. So beside the top cover and bottom cover, this is the customized LED board of the AECG. And this is actually what make happen. And also we have a special lens for it. So these kind of the works is from joint project long ago with a notable electronics consumer electronic manufacturers. So these kind of the concept or idea or requests can be resolved. Yeah, if you need it, and you can reach out WellTech for it. And another news is that in the second half this year, we'll be launching a smart retailer modules. So beside the AECG100 main unit, the module will be offered in the shape of a finger that the smart ring can sit in. And we also consider the size available for the rings. There's a ring sockets over there. So this is the explosive view of it. So if you have a closer look, we have a LED and a PD. The PD is ready to detect the LED sampling frequency of the smart ring, and then we use the same LED sampling frequency to shoot back for sketching the right PPG waveform on the rings PD and also the signal processing hardware. And this is the example for the multi-size sockets. So if you have 10 size, so then the customized PPG window, the finger shapes will based on the smaller size, which means that there's another 9 size left. So we can prepare 9 size of the socket just for the rest of the size of your ring. So let's conclude that the design of the PPG adapter must consider enclosure of light path, shortest distance between optics of duty and simulator, and isolation between optics of the DUT. And the multi-channel PPG acquisition of the wearable device, the LED board of AECG and mechanical adapter can be customized on demand to have all LEDs and the PD get a simulation and the same signal. So overall, we would like to wrap up our webinar today by mentioning that the standard does give us a way out of it before we have to go through the clinical investigation, which is costly and time-consuming. An optical simulator is the example of the functional test mentioned in the standard. And multi-channel ECG, a PPG acquisition can be simulate and verify once the AECG100 is customized or modified by request. So all the PD of your wearable device will get the simultaneous and the same signals. Now, questions. And we also have questions from the attendee before the live session today. There's some few one, and then we'll be starting getting questions. All right, I have a live questions from Ravinder Kumar. Thanks. So any way to check the DC? So the DC is that we have we can say the ideal PD in our laboratory. So we can calibrate our DC, which is our intensity, absolute radiance and intensity. But to check the DC of the wearable devices is also works. So we can turn on our PD and using sampling feature, which is the AC. But for the DC of the wearable device, it cannot be checked. So what I'm saying right now is that the DC of the wearable device we need more information from your side to clarify your questions. But to make sure the DC of our product is repeatable and consistent, we have our own solution to make sure that. Our patient testing are still necessary, as you are saying. The ISO 80601, the 2-371 are allows for only functional tester data or found case submissions. Yeah, so they are successful case of our clients that adapting the functional tester of us using the secondary calibrations, and that works. But we don't have a absolutely answer for that, because in some cases the FDA overreview their submission, and they still think the clinical trial is the must. So I will still say the clinical trial is the guideline, is a golden answer for all the accuracy claim. But the functional tester does give you a better chance that you can save these capitals. Hope you answer your question. Thanks. Can test adapter be customized to work with signal from other product apart from ring or armband? Oh yes, the rings. Right. The armband. Yes, the armband. You mean we do have experience, like what I showed you the case study once. There's a watches, so that can be done. Yeah, for sure. Yeah, in case I didn't answer properly, you can write some more detailed questions. So armband fixtures, we did quite a few. And tell me about the PWT measurement. What model I need to be check WTT accuracy? What module are needed? So the module needed is the any PPG module of us. We have one R which have a green LED only, and have a 2R which are in IR LED available. So this is the module only give you the PPG, which is optical signal. But for the ECG is the main unit. It is the AECG with the IEC 60601-2-47 test circuit embedded. So that gives you the only ECG test capability. So with the main unit AECG and the PPG module, you can push the ECG and the PPG signal at the same time. So the answer is you just need a main console and any PPG modules. Hope my answer satisfy you. Right. All right. Thanks for asking those. About we use the photo transistor instead of photodiodes, how to test the 8090. Oh, right. I might have to get back to you on that photo transistor. Thank you, Ravinder. Yes, so I think we had this request from a research center, and I will double check. Yeah, I will definitely specify this in our answer. Right. Let me get back to you. Thank you, Ravinder. That's a good point. All right. And please keep typing, keep asking questions. Thanks. And we just need to cover in case this attender wasn't there. So there were two questions about how do you use one PD and detect RNIR LED, because you're seeing that we put one LED in the middle, and how can our one PD to detect RNIR? The answer is that this is another case study from the project with customer long ago. So that we apply a lens filter over there. So from there, they can separate the light into RA, RNG. So one PD can handle it. They can overcome this kind of the signal detections. So it's all about the optics design that included in the Well-Tech customization services. All right. So another question is that, is any AOS 6061 requirement existing for all forthcoming for PPG-based designs? The design that the best we can think of is actually from the IEC 63203-402-3. Yeah, actually it's super news from last year. So in the chapter 4.3.1, it does mention about PPG simulator testings. So it mentioned this is the schematic of the PPG simulators. So it does test, it tests the heart rate function only. So SPO2 is not included in the standard. So first you gotta make sure the wavelength is correct. And it asks the sine wave from the simulator at the voltage from 0 to 5. So in this case, ACG actually provide the AC voltage from 0 to 30 millivolts. And then you're gonna switch different frequency to test a different heart rate, and that in that case, from 0.5 to 3.5. In ACG, we can cover up to 5 hertz. For the third requirement is that you gotta read the heart rates for 5 to 4. You read it for 5 to 10 seconds, even record it for minutes to make sure the stability and accuracy. So this is the best we can think of, and it's good to share with one of you. So again, could you mention standard again? What number is this? So this is from anonymous attendee. So I only mentioned 2 standard over here. One is the A061-2-61. This is the standard for pulse oximeters. So this is including the secondary standard, also the functional tester. Here in this slide, I'm mentioning from the IECs 63203-402-3. This is the new standard from the last year, only mentioned about the a PPG heart rate sensor. And could I use this to test the power fraction consisting of the device power efficiency? It depends on current transfer ratio. Yes, I think it depends. Okay, so my suggestion is that we have a PD sampling feature in our SDK. Yeah, by the way, our product we offer free SDK. So you can automate the ACG system for end-of-line testing in your mass productions. So in that SDK offer the PD sampling raw data. So we can output all the raw data by 8 bits. So we will separate it from 0 to 255. So this is how our PD measure your LED. So you can compare your currents and make some correlation. And maybe that helps. That help you to determine your power efficiency. I think this is how I can think of the best for you. So the short answer is that we can output our PD detection raw data for you to qualify your power efficiency. Yeah, compare with your LED drive currents. What type of lens you are used? Oh, that's actually a patent. As a patent technology that we partner with our clients. So bear with me that I could not just share about that. Yeah, over this public occasion. Thank you, Ravinder. All right. Thank you, everyone. We'll be closing our webinar in 2 minutes. Thank you for all the questions and your patience and staying the questions. We are very, very honored and loved it. Thank you for supporting WellTech with your time and with your attentions. So this is the second webinar of 2025 this year, and there will be more just coming up as we've been evolving. We've been learning with all the medical device manufacturers, and assume as the more trendy technology over there, we'll be so happy to share with every one of you. So Thank you for your time spending with us. For that, I hope session have shed lights on leveraging the accuracy and the performance of the PPG wearable device, and your feedback and the question are invaluable to us. So feel free to reach out us anytime afterwards, even me or our team through our service mail service@welltech.com. And we'll be looking forward to talking to you offline for sure. I'm Stefan. You all have a wonderful day. Thank you.